Okay, good morning. All right, so tomorrow night is the exam, 6:30. Elliott Hall of Music. Find out where you're supposed to go. Know your seat number. Know your section number. And we're going to do our best to start the exam on time at 6:30. So that means if you show up, you don't know where to go, we may start without you. So make sure you get there early enough, find out where you need to go, and get seated. And the reason is because there's an exam coming in right after us. There's a big chemistry exam right after us. We can't hold up the show for very long. We got to get started. So again, find out where you need to go and get seated as soon as you can. Let's take a look at the calendar here. Today we're doing review. Tomorrow's the exam, of course. There's no homework due tomorrow night. And also Friday, there's no class because of the exam. We owe you a day, so you get Friday off. All right? Okay, let's talk about the exam. Well, based on the old exams, you know the format. It's a 12 multiple choice. Covering everything up to lesson 14. That was last Friday's stuff. Okay, so what we're going to do here is, there's a lot to know, of course. Oh, by the way, let me bring the computer back here for a moment. There is a study guide here posted on the course webpage. I'm sure many of you have seen this already. This is put together by Professor Phillips, who teaches the later section of this course. And this is a wonderful stuff here. Look over it. It has everything that we did. So again, this is Professor Phillips' wonderful work. Take advantage of it. All right, so of course there's a ton of stuff. We need to focus on things that you should focus on. So let's look at the topics that I think you should focus on. You need to know how to put together a plane, the equation of a plane and what you can do with it, this kind of thing. Equation, we all know this thing here. What is the equation of a plane? Some constant times x minus x0 plus some other constant y minus y0 plus some other constant z minus z0 equal to 0, right? This came out of a dot product. What are a, b, and c? The normal vector, good. So that's the vector that's perpendicular to the plane. Okay, let's do an example finding the equation of a plane. This one I'm going to take from Spring 14, number 8. Here we want to find the equation of the plane containing 3 points. Okay, so what do? We need a normal vector. How do we find that? And cross them, right? Exactly. You find two vectors in a plane. So if I call the first vector going from the first point to the second point, from 103 to 110, the first vector is 0, 1, minus 3. Right? There's no x change. There's a change of 1 in y and a change of negative 3 in z. And the second vector, I can use the vector going from the first point to the last point. So the vector would be 0, 1 minus 0 is 1, and then 1 minus 3 is negative 2. A normal vector is going to be perpendicular to both of these things. So the normal vector is simply A cross B. Can I do B cross A? Yeah, that's also a normal vector. They point in different directions. Either way is fine. And of course, you need to remember how to do the cross product. Okay, so let's see. The I component would be negative 2 minus 3. So that's a 1. J would be 0. K would be 0. The first column being 0 makes the second two components 0. Very nice. That's a nice vector, just an I vector. Then you use 1 point to form this plane. Pick any of the three points given to you. Any of the three would work. So I'm going to arbitrarily choose the first one. That's my x0, that's my y0, and that's my z0. And that's my big A, big B, and big C. So the equation of the plane is very simple. A times x minus x0 plus a bunch of zeros equal to 0. And at the end of the day, we get x is equal to 1. All right? You got to remember that in 3 dimensions, the missing variables mean that all of the numbers for those 2 variables are included. So this is a plane that intersects at x equal to 1 with z and y being all real numbers. It's a big, infinite plane. Okay? All right, so let's talk a little bit about surfaces. And as an example, let's look at spring 15 number 3. So here they gave you an equation, x squared minus z, y squared minus z is equal to 0. And you have to identify this thing. And your choices are hyperboloid of 1 sheet, hyperboloid of 2 sheets, a sphere. I'll write this down. Okay, so those are your 5 choices. One of these we can immediately rule out. Which one is that? Sphere, right? What's wrong with this? How do you know it's not a sphere? Z is missing a square, right? And the signs are not right either. So that's automatically out. Now the rest of these, upon first glance, are all possible. So what do we do here? It really boils down to finding the traces of stuff. Start with Z is equal to K, for example. What shape is this? I hear all sorts of shapes. Hyperbola, right? Right? Okay, if you didn't know that, make sure you know that by tomorrow night. Okay, so if K is positive, let's stick with K being positive for the moment. If K is positive, then x squared minus y squared. These are hyperbolas that sit on the x-axis. Something like that. The reason is because this thing cannot have a y-intercept. Because if you make x equal to 0, then you get negative y squared is equal to k. If you assume k is positive, that can't happen. So we got this kind of shape. And if you look at if k is negative, then these switched around, right? And then we have hyperbolas that sit like that. And then there are 2 straight lines when k is exactly equal to 0. They will both show up on here and here. This is k equal to 0, exactly 0. And we covered this shape in class when we first talked about the surfaces. This is that saddle shape, right? The Pringles chip shape. So you got hyperbolas that you have above the plane, this kind of hyperbola. Below the plane, this kind of hyperbola. So you have a saddle kind of shape thing. Or Pringles. It's the same shape. And now the important thing is, what do we call that shape? What is that shape? Is it A? No. B? D? Yeah, that's it. That saddle thing is the hyperbolic paraboloid. Okay, paraboloid comes out if you take the traces, let y equal to k or z is equal to k. For example, if x is a constant, x or y equal to k, sorry. If x is a constant, then here you have y squared and z. These are parabolas. So that's where the paraboloid part comes in. If you make y constants, then you have x squared and z. These are more parabolas. Okay? Elliptic is if these things are ellipses, then we would have an elliptic paraboloid. A hyperboloid would be hyperbola for all the traces. And a sphere, you know what it is. So on the exam, we cannot ask you to sketch anything. So you might be asked to, we could give you a bunch of graphs and a bunch of equations, and then you're supposed to be able to link one equation to a graph. Or we could give you one equation and 5 graphs and say which graph goes with that equation. Or vice versa. We could give you 5 equations and 1 graph and ask you to find which equation goes with that 1 graph. So for tomorrow night's exam, the name of that surface is not important. What's important is that you could at least come up with a reasonable visualization given the equation, or given the graph, be able to use traces to recover the equation. Make sense? Yes? Okay, let's see. What's the next thing we'll look at? Aha. Let's talk about arc length. So arc length, this is what happens when you have a space curve, a 3-dimensional one here, x, y, and z, and they're each a function of a parameter t. And let's say t is going between a and b. All right, so now you need to know the formula. What's the formula? Perfect. This guy here. And I like to remember this as simply the integral of the magnitude of the derivative. Because physically, what this thing here, this is the speed. Speed times time gives you distance. Integration means you accumulate all of these distance from beginning to the end. This is the formula I prefer to remember. Okay, let me find an example here. Fall 15 number 3 is a good one to look at. Here we're looking for the length of that curve from t is equal to 1 to t is equal to e. And this should be one of those problems that if it shows up, you should be able to get it right. This is very straightforward. There's nothing tricky about it. If you know the formula, this should be a slam dunk. All right, r prime, this is 2. Here we get, what do we get? 2 over radical t. That's 1 over t. Let's find the magnitude of this. Square sum of the squares under a root. 4 plus 4 over t plus 1 over t squared under a radical. And we'll eventually have to integrate this thing. So let's do something about this, make it simpler before we do the integration. Let's put all of these guys over t squared. top here just so happens to be a perfect square, 2t plus 1, the quantity squared. Downstairs is t squared. Taking the square root, remembering that the magnitude is always positive, we keep the positive root. So this turns out to be 2 plus 1 over t. And that goes into here to be integrated, and then you integrate from 1 to e. So the last step is just integration. Two t plus natural log of t, 1e, 2e plus 1 minus 2 plus 0, so this is what? 2e minus 1. Okay? And like I said, this is the kind of problem that you should be happy when you see it. This is very, very easy to do. This is 8 points in your pocket. Okay, now slightly harder stuff. Let's talk about curvature. Let's look at spring 14. Well, first of all, remember the formula for curvature? There are a couple of forms. The one that we use in class most of the time is the most convenient one to use. You remember that? Magnitude of t prime over magnitude of r prime. Right? T prime is how much turn you need to make. R prime is how fast you're going. If you're going straight, then there's no t prime. So 0 over something, that's 0 for a straight line. What is t? What's capital T? It's a unit vector. What? Tangent, unit tangent. Okay, so given a space curve, we need a unit tangent, and then we need r prime. R prime is what you would need to find the unit tangent in the first place. So it really boils down to finding that. Okay, example. We'll look at spring 14, number 10. Curve is t, 1 e to the t, and we want to find the curvature at t equal to 0. This is the key here, right? You find this, you find t prime, then the rest of this is very simple. So let's get to t first. R prime is 1, 0, e to the t. And we're looking at the curvature at a specific point. And now we can put in that t just to make things a little bit more manageable and less cluttered. So let's go ahead and find out r prime at that particular moment. So this turns into 1, 0, 1, and the magnitude of that is radical 2. Okay, so that's the length of the tangent vector. If you divide the tangent vector by the magnitude, that gives you your unit tangent. So here, because we need to take the derivative later, we need to leave t in there. We'll use this later, but now we gotta get the t into here, little t. So here's our vector r prime. Magnitude of this is that, right? 1 squared plus e to the t squared all over a root. So this is 1 over this thing, 0, e to the t over 1 plus e to the 2t, all over all under a root here. Now we need a derivative of this thing. The first one, you can look at it as 1 plus e to the 2t to the negative 1/2. So derivative is minus 1/2, 1 plus e to the 2t to the negative 3 over 2 times 2e to the 2t. Middle component is 0. Very nice. The last one here, you're just going to have to use the quotient rule and get through it. All right, so the last one, I'll put it down here at the bottom. Quotient rule. So we got 1 plus e to the 2t to the 1/2 times the derivative of e to the t minus e to the t times derivative of radical 1 plus e to the 2t all over this thing squared. Okay, so this looks a little busy here, but that should be what you get by simply applying the quotient rule with the last component. Let's simplify this thing a little bit. First one, there's not much to do except that 2 and negative 1/2 will cancel. So it's negative of e to the 2t over 1 plus e to the 2t to the 3/2. The last component here, 1 plus e to the 2t to the 1/2 e to the t minus, we have a 1/2 and a 2, and then e to the t and e to the 2t, so there's an e to the 3t there, times 1 plus e to the 2t to the minus 1/2. Yeah, that one is kind of annoying, but hey, it is what it is, right? We can simplify the last one a little bit more. I could multiply top and bottom by 1 plus e to the 2t to the positive 1/2. What that does is make this to the first power, make that a 1, and make this 1 plus e to the 2t to the 3/2. And that may not be strictly necessary because we're going to plug in a value for little t anyway, right? But it just makes things a little bit more manageable. And actually, we can simplify this even more. Look, this e to the 3t minus e to the 3t. So this is e to the t over 1 plus e to the 2t to the 3 over 2. All right, so don't forget what we're doing this for. We're looking for our little kappa, our curvature. Numerator of that is t prime, the magnitude of t prime at that little t. At t equal to 0, t prime is equal to negative, that's a 1, that's a 2 to the 3 over 2, 0. Here, this is that's a 1 also, 2 to the 3 over 2 down here. Find the magnitude of that. This thing squared. Nothing. And this thing squared. Okay, 2 to the 3 over 2, squaring that just makes that 2 to the 3rd. So this is 1 over 8, 1 over 8. Added together is 1 over 4. Square root of that is 1 over 2. Okay, now kappa is very easy. One over 2 over magnitude of r prime at 0 is radical 2. We got that earlier. And so this turns out to be 1 over 2 radical 2 downstairs. All right? Okay, the algebra aside, you just got to find your t prime. Once you get your capital T, take the derivative, find t prime. You would have r prime anyway, so that's really the thing that you need to find for a problem that involves a curvature. Let's look at a couple limit problems. The first one I want to look at this is spring 14, number 1. x to the fourth minus y to the fourth plus xy all over x squared plus y squared. The key of the limit problem is limit must be the same. From all paths of approach. So the easiest thing to do here is to find at least two different limits. Choose two different paths, at least two different paths, find two different limits, then the limit doesn't exist. Okay? So do the easy things first. Approach along the x-axis, approach along the y-axis like we did in class. If you approach along the x-axis, then that means y is always equal to 0. So the only variable that's left here is x. Upstairs would be x to the fourth, nothing, nothing, x squared, and nothing here. So this goes to 0, right? Let's do the next easiest thing. Approach along the y-axis. That means x is always equal to 0. And so therefore, the only thing that's allowed to change now is y. So we get minus y to the fourth over y squared which also goes to 0, right? Does that mean the limit is 0? No. Just because we found two that give us the same number does not guarantee a limit. So we got to find another one. What's another one that we can do? A simple one. Yeah, let's just do y is equal to, let's just try y equal to x. We can do y equal to mx if you want to, but let's just try y equal to x and see what happens. So y is going to become an x, therefore the only thing that really depends on is x. So this is x to the fourth minus y to the fourth, but y is x now, plus x times x, that's x squared. Downstairs is x squared plus x squared, because y is equal to x. So this time the limit turns out to be x squared over 2x squared. This is 1/2. Okay, so we broke it, right? We found at least two paths that give us different limits. Therefore, the limit does not exist. If this turns out to be 0 too, then you got to try another one. Y is equal to x squared maybe. But we're not going to make you do that on the exam. The limit we give you, you should be able to find, you should be able to draw a conclusion within 3 steps. So don't worry too much. There goes my microphone. All right, so, yeah. When would I stop? I would stop and go back to the expression and find a way to not having to do that. Maybe I can factor something. Maybe I could use a squeeze theorem here and there to come to a conclusion without having to try all paths. Because, that's a very good point. When would you stop? In principle, you never stop, right? Because we have to check every single way of approach, and we can't do that. So that's the time you want to go back and find a way to rewrite the expression. And you've seen a few of those on the homework where things can cancel out and to give you a limit. Let's do a differential problem. Let's look at fall number 11, number 5. In here, we're dealing with the surface area of a rectangular box. And the surface area that's given in the problem is 2xy, right? Xy would be the bottom and the top, two of those, plus 2yz plus 2xz. There's 6 faces. You add them all together. That gives you the surface area. Here we measured x to be 10 centimeters, y is 20 centimeters, and z is 30 centimeters. And the measurement errors are 0.1 in each of these. Here we want to estimate the maximum error in the surface area. Okay, so first thing here is to find the differential. The differential, in most of the examples we did with the 2 variables. 3 variables, the same thing. D big S is the partial derivative of S with respect to x times dx. Partial S, partial y, regular dy, plus partial S, partial z, regular dz. That's the differential, which is closely related to the tangent plane. Let's find these partials first. X, 2y, plus nothing, plus 2z, dx. Partial with respect to y, we get 2x, 2z, nothing here. Last thing here, 2y plus 2x, dz. And remember, these d's, these are our errors. And the variables without a d attached to them, those in this context are what we think they are. We measured y to be 20, we measured z to be 30, for example. So these are what we think they are. The d's are the errors that we know that's included. So here we go. We get 2y, that's 40. 40 plus 60, that's 100. Error is 0.1 being x. 2x is 20. 2z is 60, so that's 80. The error in y is 0.1. 2y is 40. 2x is 20, so that's a 60. Times another 0.1 because of the error in z. Here we get 10 plus 8 plus 6. That's 24. 24. Okay? And as you remember, the propagation of error sometimes comes out quite surprisingly. Seemingly tiny errors in each of these, in the end, accumulates to something very big in what we're calculating. All right, so differential. Basically, if you can get this equation here, interpret things correctly, you should be okay. Let's do one more thing dealing with chain rule. The key in the chain rule problem, of course, is to make sure, draw the tree diagram. If the tree is right, you'll be fine. Let's look at spring 14, number 4. Z is an unknown function of x, y. X is s squared minus r, and y is r squared s. We don't know what z looks like, but we know the partials. And we want to find the partial derivative of z with respect to s. Get the tree correct, and everything else should just be a matter of following the tree correctly. Okay, so this is the key piece of stuff you need. Okay, we're running out of time. I'll finish this before I upload the notes. But the next thing to do is to remember that each time there's a split, there's a partial derivative. So I'll complete the example, and you'll see the completed one in a little bit. All right, that's it. See you tomorrow night.